All right, so now we're going to have a new definition. So we start with integers a and b and the natural number n. Okay, so these could be any integers and a and b and any natural number n. We say that a and b are congruent modulo n, if n divides a minus b. We write this as like this, right? So a is congruent to b mod n. Or a and b are congruent mod n. On the other hand, if n does not divide a minus b, then we write that a is not congruent to b mod n. Okay, so this notation includes a few parts. It includes a, it includes b, and it includes n. And what we're saying here is that a is congruent to b mod n. In other words, n divides a minus b. Let's do some examples. So first example is 9 is congruent to 1 mod 4. Why? Well, 4 divides 9 minus 1. That is, 4 divides 8. That's true. 4 divides 8. In other words, 4 divides 9 minus 1. So therefore, 9 is congruent to 1 mod 4. Another example. 6 is congruent to 10 mod 4. Since 4 divides 6 minus 10, that is, 4 divides negative 4. 17 is congruent to negative 4 mod 3, right? So a and b are allowed to be negative. They have to be integers. N has to be a natural number, so it has to be positive. But a and b could be negative potentially. So 17 is congruent to 4 mod 3. Since 3 divides 17 minus negative 4, that is 3 divides 21. All right, 17 minus negative 4 is 21. 14 is not congruent to 8 mod 4. Why? Since 4 does not divide 14 minus 8. That is, 4 does not divide 6. Now, here's an important note that we're not going to prove. The book discusses this a little bit, but here's a very an alternative definition of congruence modulo n, and it is in fact equivalent to the original definition that we gave above here. It's not easy to see that they're equivalent definitions, and we're not going to get into how we show that they're equivalent definitions, but they are. So if a and b are positive, then to say that a is congruent to b mod n, that is the same thing as saying that a and b have the same remainder when divided by 4. Sorry, when divided by n. So the idea is that when we say a is congruent to b mod n, what we're saying is that a divided by n leaves the same remainder as when b is divided by n. Same remainder that b would have when divided by n. Now, we have notation for this, or we have a way of expressing this in Java, right? In Java, when we say a is congruent to b mod n, how would we say that in Java? Let's assume that a and b are positive. We would say that in Java as follows. A mod n is equal to b mod n, meaning if I take a and divide it by n, the remainder that I would be left with is equal to the remainder that I would be left with if I take b and divide it by n. So this is a nice alternative definition, but it's hard to see how it's actually equivalent to the original definition, but it is in fact equivalent. For example, we know that 6 mod 4 is equal to 2, right? In Java, 6 mod 4, try it out, it's 2. 10 mod 4 is also 2. So we have two numbers, 6 and 10. And 6 mod 4 is 2, and 10 mod 4 is also 2. So therefore, 6 is congruent to 10 mod 4. All right, now let's do a proposition involving congruence, and let's do a proof of it, of course. So let a and b be any integers. If a is congruent to b mod n, then a squared is congruent to b squared mod n. That's the claim. That's what the proposition claims. let's do an example first, just to make sure we understand what the proposition is saying. So we know that 6 is congruent to 10 mod 4, right? We had that example just before. 6 is congruent to 10 mod 4. What this proposition tells us is that from this fact, we can derive the following. We can say that 6 squared is congruent to 10 squared mod 4. That is, 36 is congruent to 100 mod 4, right? So, it's not obvious that 36 is congruent to 100 mod 4. It'd take a little bit of work to determine that. But since we know that 6 is congruent to 10 mod 4, and 36 is just 6 squared, and 100 is just 10 squared, we can conclude that 36 is congruent to 100 mod 4, at least if we assume that the proposition is true. We don't know that it's true. We have to prove it. So let's go ahead and prove the proposition. We're going to use for this, we're going to use direct proof. And generally, when you're trying to write a proof and you don't know where to start, it's often good to start by trying to do direct proof. And if you can't figure out a way how to make it work, then try contrapositive proof, and then you can try other methods of proof that we'll learn about. Unless you're told specifically to use a certain type of proof, or unless it's a type of problem that is very amenable to specific types of proof. So certain kinds of problems are very amenable to solving, via induction, which we didn't learn about yet, for example. But for, in general, where you have no indication of where to go, it's good to start with direct. So let's do a direct proof. So in a direct proof, we're going to assume that A is congruent to B mod n, and we're going to show that that forces A squared to be congruent to B squared mod n. So suppose A is congruent to B mod n. All right, so now we have to go back to the definition and see what does this tell us? Okay, so go back to the definition. What this tells us is that n divides A minus B. So then n divides A minus B. Okay. Now, what does it mean to say that n divides A minus B? Well, we have the definition of divisibility. And according to that, when we say that n divides A minus B, what that tells us is that A minus B is equal to n times C for some integer C. Now, we are trying to prove something. We are trying to prove that A squared is congruent to B squared mod n. In other words, what we have to do is prove that n divides A squared minus B squared. Now, here we have A minus B. We can convert this into A squared minus B squared by multiplying A minus B by A plus B. So what I want to do here is I'm going to take A minus B, multiply it by A plus B, and then I'll multiply the other side by the same thing. Now, if I do the multiplication, I come out here with A squared minus B squared equals n times C times A plus B. So what does that show us? Well, we have A squared minus B squared is equal to n times an integer, right? So C times A minus B, not the n. C times A minus B is an integer. Now that's multiplied by n. So we have A squared minus B squared is equal to n times an integer. Thus, A squared minus B squared is equal to n times D, where D is an integer. Specifically, D is equal to C times A plus B, which is an integer. So what does that let us conclude? Well, that tells us that n divides A squared minus B squared, because A squared minus B squared is equal to n times some integer. So thus n divides A squared minus B squared. Oops, sorry, I need to have parentheses here. Hold on. All right, so n divides A squared minus B squared. And therefore, based on the definition of congruence, we have that A squared is congruent to B squared mod n. So let's review the proof. We were doing a direct proof, so we started by assuming that this is true, and our goal was to show that this is true. So we started with, suppose A is congruent to B mod n. The consequence of that is that n divides A minus B. The consequence of that is that A minus B equals n times C for some integer C. Now, we know our goal is to show that A squared is congruent to B squared mod n. Now, the step before that has to be that n divides A squared minus B squared, right? In other words, the fact that we have this step here allows us to get to the conclusion. So we need to have this step here. The step before this step, right before this, we have to say that A squared is a squared minus b squared is equal to n times d for some integer d, right? In other words, in order to show that n divides a squared minus b squared, we have to show that a squared minus b squared is equal to n times an integer. So the idea is we have a minus b equals n times c, and we need to show that a squared minus b squared equals n times d. Well, if we take, so the idea is we need to somehow take this a minus b and put it into the form of a squared minus b squared. So how can we do that? Well, we can multiply both sides by a plus b, right? Multiply both sides by a plus b. That gives us here a squared minus b squared. And then on this side, we have this. And then what we see is we have n times c times a plus b. And that is an integer, right? So we have a squared minus b squared is equal to n times d. And that leads to the conclusion. So I mean, I didn't show this in the progression of the slide, but right, really when writing a proof, you typically start from the beginning, write, what you can determine so far. Then it's often helpful to to start from the bottom also. Well, in addition to starting from the top, it's also helpful to start from the bottom and work your way up. And the goal is to meet, right? The goal is to build a bridge between the beginning of the proof and the conclusion of the proof. And so the creativity that's required in proofs comes in the middle, right? Usually the first step or two is straightforward. One thing leads to another thing, and the end usually one thing leads to another thing. But again, the difficulty is in the middle to connect the beginning and the end, and that's where some creativity is needed. I mean, this is not, you can't design a computer that can, you can't make a computer program that can prove any arbitrary proposition. You can make a program to prove a very specific classes of propositions, like specific types of propositions, maybe. But to make a computer that can prove any proposition you give it, I don't think it's ever going to be possible to do. Or it seems very, very unlikely that it would ever be possible to do, because it requires we don't really know. It's just some creativity in there. Anyways, we're not going to, the proofs that you're going to have to write for this class and on the tests are not going to require crazy amounts of creativity. They're all going to follow similar patterns, but still there is some creativity needed. Okay, let's do one more proposition involving congruence of integers. And here it is. Suppose a and b are integers and n is a natural number. If 12 times a is not congruent to 12 times b mod n, then n does not divide 12. Okay, so that's a very, I mean, it's just, it's really hard to see what to do here. So, if we would do a direct proof, right? If we would try doing direct proof, what would happen? So we would start with 12a is not congruent to 12b mod n, and our goal would be to show that n does not divide 12. There's no obvious way to go from here to here, right? There's no obvious way to bridge that gap. So we're going to try using contrapositive proof. Okay, so now in a proof by contrapositive, remember, we assume that this is false, and our goal is to show that this is false. And that is proving the contrapositive, which is therefore proving the original proposition. Okay, so what we want to do is prove the following. If not n does not divide 12, then not 12a is not congruent to 12b mod n. In other words, if not this, then not this. Okay, this is not good English, right? It's not good English to use because this is not an English word, but it's just a little shorthand. It's helpful sometimes for writing it. Okay, so all right. So what do we want to do? So we're going to start out by supposing this, and then we're going to try to conclude that this. Okay. So suppose that it is false that n does not divide 12. Again, suppose it is false that n does not divide 12. In other words, that is, suppose that n does divide 12. Right, again, it is false that n does not divide 12. That means n divides 12. All right, so what do we know if n divides 12? So 12 is equal to n times c for some integer c. Now our goal is to do something with 12a and 12 not being 12a not being congruent to 12b, right? So in other words, it's going to be 12a minus 12b, or n is going to, we want to think about n dividing 12a minus 12b. So how can we take this 12 and turn it into 12a minus 12b? Well, we can multiply the 12 by a times b. And then we have to multiply the other side also by a times b. So we have this. In other words, we have 12a minus 12b equals n times c times a minus b. So what do we have here? We have 12a minus 12b is equal to n times an integer, right? N times an integer. Thus, 12a minus 12b is equal to n times d, where d is an integer, namely d is equal to c times a minus b, and the result is an integer. All right, so now what do we know? Thus, therefore, n divides 12a minus 12b, and therefore 12a is congruent to 12b mod n, meaning that it is false that 12a does not divide, is not congruent to 12b mod n. Again, it is false that 12a is not congruent to 12b mod n, and that's what we proved. So we proved that if we suppose that this is false, then this has to be false. So what did we do? We proved the contrapositive of the original proposition, and therefore we have proved the original proposition itself. Now let's just go through this proof to see why we did what we did. So we started by supposing this, and in other words, n does not divide 12. And in other words, that means 12 is equal to n times c. All right. So far, until here, it was straightforward. At this point, we might pause here, right? We might pause here and start working our way up from the bottom. Our goal is to show that it is false that 12a is not congruent to 12b mod n. In other words, what we're trying to show is that 12a is congruent to 12b mod n. Now, in order to show that, we have to show that n divides 12a minus 12b. And in order to show this, we have to show that 12a minus 12b is equal to n times d. So we need something with 12a minus 12b. And what we have is 12 equals n times c. So we need to get this 12 to become 12a minus 12b. How did we do that? Well, we multiplied the 12 by a times b. And then, of course, we had to multiply this by a times b as well. And then we got 12a minus 12b equals n times c times a minus b. And then so what we have is 12a minus 12b is equal to n times an integer, which told us that n divides 12a minus 12b, which told us that 12a is congruent to 12b mod n, in other words, which is what we wanted to find. All right, that's the end of this week's videos on proofs. Next week, we will talk about other kinds of proofs.